Alrighty, so I'm just going to move through this review and just talk through it, and maybe it's helpful. Shouldn't be not helpful, that's for sure. My name's Alban, and I think math is okay. Okay, at each point indicated on the graph, determine whether the value of the derivative is positive, negative, zero, or the function has no derivative. Okay, well, we're looking for the original function to be increasing, decreasing, maybe be constant or have a horizontal tangent, or perhaps have a corner or something, right? The original function is going to be increasing, decreasing, constant, or have some problem. And that way we can look at the derivative. So this is testing your understanding of how the derivative relates to the original function. At point A, looks like we have a corner. So the derivative does not exist. At point B, it looks like my function is decreasing. Right? It's going down. If I had a tangent line, it would have a negative slope, and therefore the derivative is negative. At C, it looks like I would have a horizontal tangent there, and therefore I think the derivative there should be zero. At D, the function is increasing. If I drew a tangent line, it would have a positive slope, and therefore I believe that the derivative should be positive. And at E, I think that it would also be zero, right? Because there's a horizontal tangent. Now, of course, there's a couple other things we didn't see here. Like, for instance, if you had a cusp, a point like that, F, the derivative would not exist. And of course, if you have, a vertical tangent, sometimes you can have a vertical tangent where the derivative does not exist. So don't forget about a vertical tangent or a sharper corner, which is called a cusp. Moving on to number 2, multiple choice. They gave us a function. They want us to know, they want to ask, or they want us to know which of the following will calculate the derivative of f of x. In other words, which one of these gives me f prime? Derivative of f of x, excuse me, is just f prime. So I'm trying to match this up with the limit as h approaches 0 of f of x plus h minus f of x divided by h. Well, it's definitely not that. It's definitely not that because those don't have a limit. So there's no way it could be either of those because there's no limit. So those are just maybe average rates of change or something. So it looks like to me that C is the one we're looking for. It just varies from B a little bit. This one, it looks like they did f of x and then added h. And over here, it looks like they actually plugged x plus h into the function to get 2 times x plus h all squared plus 4. So C is the correct one there. 3. Here's a function. Find the average rate of change of this function on this interval. That's just the change in y over the change in x. So that's going to be f of 4 minus f of 1 divided by 4 minus 1. All right, let's find f of 4 over here. F of 4 would be 4 cubed plus 2 divided by 4, which is 66 divided by 4, which is 33 divided by 2. Okay, and let's find f of 1. F of 1 would be 1 plus 2 over 1, which is 3. So we're going to have 33 halves minus 3 divided by 3, which is 33 minus 6 over 2 divided by 3, which is equal to, right, because here 6 over 2 is the same as 3, so I just got a common denominator. 27 over 6, or wait, 27? Yeah, 27 over 6. Divide that all by 3. and you get 9/2 or 4.5, I think. So hopefully that's correct. So I made a mistake. That'll be 4.5. Instantaneous rate of change of f of t when t equals 2, that's just f prime of 2. So we need to find f prime of x first. Now, f of t is t cubed plus 2 divided by t. When you only have one thing in the denominator, I would recommend that you simplify this first and not use the quotient rule. So we could say that f of t is equal to t squared plus 2/t. So f of t is just t squared plus 2t to the negative 1. So therefore, f prime of t would be 2t minus 2t to the negative 2. Plugging in 2, f prime of 2 should be 2 times 2 minus 2 times 2 to the negative 2. 2 times 2 is 4. And it's going to be 4 minus 1/2 because this is 2/2 squared, which is 2/4, which is 1/2. So we should end up with 3.5 for the instantaneous rate of change at 2. Okay. Number 4, find the equation of the tangent line when x equals 2. Equation of the tangent line is simply y minus the y value at 2 equals the derivative at 2, the slope, aka, times x minus 2. Right? That's just kind of the calculus version of the point slope form of the line. So we should end up with y minus 3 equals -1 times x minus 2. We could leave it that way, or we could write y equals -x plus 5. Either way would be fine. Find the equation of the tangent line to the graph of this when x equals 2. Okay, well now we need to find f prime. So f prime of x is going to be 2x minus 2. Therefore, f prime of 2 is going to be 4 minus 2, which is 2. So that's the slope. I also need to find f of 2, so I have a y value. F of 2 would be something like 4 minus 4 minus 3, which is -3. So now I can write y minus -3 equals 2 times x minus 2. Or I could write y plus 3 equals 2 times x minus 2. I should either write that, or I could write y equals 2x minus 7. So either that or this would be an appropriate way to write the equation. So remember, for a tangent line, you need a point and you need a slope, which you're going to get from the derivative. Once you have a point and a slope, you can just write the equation from that. Number 6. Okay, we've got a piecewise function. They want you to find all possible values of a and b such that f of x is differentiable. Okay, if it's going to be differentiable, by the way, I have a linear function and I have a quadratic function, and they need to meet up so that the y values are equal and the slopes are equal, right? So it needs to be smooth and connected there. It needs to be differentiable. So essentially what I'm looking for is I'm looking for these two to be equal at x equals 1, and also f prime to be equal at those values. So let's find f prime first. F prime of x is always a good thing to find if you have a piecewise function. You want to look at differentiability. So f prime of x would just be a for x is less than 1. Okay, we can't say less than or equal to because sometimes the derivative might not exist at that point. So we're just going to say less than 1 for now. And here it would be 2bx plus 1 for x is greater than 1. Okay, so now what we're going to do is plug 1 into our original function to make sure the y values match, and then plug 1 into our derivative function to make sure our slopes match. Okay, So that should give us two equations. So we'd get A equals B plus 2 if we plug 1 into our original function. If we plug it into the derivative, we get A equals 2B plus 1. So now we can just use some algebra to solve. I'm just going to subtract the bottom equation from the top equation and get 0 equals negative B. Bottom equation, so I'm going to subtract this. Negative B plus 1, so B equals 1. And plugging that back in, I should get A equals 3. Okay, so that means that 3x and x squared plus x plus 1, if I plug in 1, I should get the same value. And if I plug in 1, I'm going to get 3 for both of those. So that means it's continuous. And then the derivative would be 3 and 2x plus 1. So if I plug 1 into that, I should also get the same thing. And I do. I get 3 for both of them. So it looks like I have solved this thing correctly. Lovely. All right, let's look at 7. Let H equal F times G. Find H prime of 2. Oh man, this is just a classic product rule. Well, H prime of X is simply going to be F of X times G prime of X plus G of X times F prime of X. That's the product rule. Very obvious product rule right there. And so if we want to find H prime of 2, H prime of 2 is going to be F of 2 times G prime of 2 plus G of 2 times F prime of 2. Okay, so we can just read those values off the graph now. I'm going to write it down here and then erase it, I guess, but H prime of 2 would equal, so F of 2 looks like is right here. So F of 2 is 2, so that'd be 2. G prime of 2 would be the slope at 2 right here, and the slope of 2 at 2 looks like it's up 2 over 1, so also 2, plus G of 2. So G of 2 is the y value there, which is negative 3. And F prime of 2 is the slope of F here, which is negative 1. So it looks like H prime of 2 is going to be 4 plus 3, which is 7. So that looks like C. Okay, so we're just basically using the product rule and then plugging things in by looking at our graph. Okay. Number 8, it asks us what G prime of 3 is. That would be what is the derivative of G at x equals 3, which is right here. So G prime of 3 does not exist. Reason being there is a corner there. So there's no way to draw a tangent line because we could draw a tangent line in any number which way. So we don't really know how to draw that basically. Okay. Moving on to number 9. Suppose f and g and their derivatives have the following values at x equals negative 1 and x equals 0. Okay. Evaluate the first derivative of each of the following combinations of f and g at the given value of x. This is a great problem because there's nothing that is super hard like mathematically about this, but I mean like computationally, but the actual mathematics, it's testing your knowledge of that. So here we can see that we need to use the product rule. So the derivative of this would be 3f prime g plus 3g prime f. Maybe it'd be better to just keep the 3 out front and say, well, it's 3 times, and then f g prime plus g f prime, right? First times the derivative of the second plus the second times the derivative of the first. Okay, so plugging in negative 1, okay, f of negative 1 is 0. G prime of negative 1 is 1. G of negative 1 is negative 1. And let's see, f prime of negative 1 is 2. So that's going to end up being 3 times -2, which is -6. Okay, this looks like a quotient rule. Low D high. Low D high minus high D low. The derivative of g of x plus 2 is g prime of x plus 0. And that's all going to be over g of x plus 2 all squared. Okay, they want us to find it at x equals 0. So we're going to be looking at this row right here to get our values. So g of 0 is -3. So it's going to be -3 plus 2 times, I'll zoom in a little bit here, f prime of 0. F prime of 0 is -2 minus f of 0, which is -1. So I'm going to do plus 1. And then g prime, which is 4. Okay, and that's all divided by g of 0, which was -3 plus 2 all squared. So now we're just going to simplify that. That's going to be 2 plus 4 divided by 1, which is 6. Okay, finally, C, we've got a composite function here. So they're testing your knowledge of the product rule. Pencil stopped working. Product rule, quotient rule, and now composite function. Take the derivative, so the chain rule. Take the derivative of the outer function, leave the inner function alone. Then multiply by the derivative of the inner function. The derivative of x plus f of x is 1 plus f prime of x. Okay, so we're going to get g prime of 0 plus f of 0 times 1 plus f prime of 0. And that is g prime of 0 plus f of 0. F of 0 is, what is f of 0? F of 0 is -1. Just moving to a different location. So let's see here. 0 plus f of 0. F of 0 is -1, so it's g prime of -1 times 1 plus f prime of 0. So 1 plus -2. Okay, g prime of -1 is 1, so it'll be 1 times -1, which is -1. Okay, now this one, what we want to recognize here, they want us to find the derivative, but what we want to recognize here is that we need to use the product rule. And within the product rule, we're going to have to use a little bit of a chain rule because we have x plus 1 inside of the square root function. So let's go ahead and rewrite this as y equals x to the 4th times x plus 1 to the 1/2. So when we do the product rule, we're going to get first times the derivative of the second, and the derivative of the second requires us to use the chain rule, right? We're taking the outer function here is blob to the 1/2 power, so we have 1/2 blob to the -1/2, and then we need to multiply by the derivative of x plus 1. Well, it turns out the derivative of x plus 1 is just 1, so we're not going to worry too much about that, but we need to be thinking about it. So first derivative second plus the second times the derivative of the first. Now we're done with the calculus. Problem is, this looks nothing like any of our choices. So we need to see if we can simplify it into something that looks like one of our choices. Okay, so first of all, this becomes x to the 4th over 2 times the square root of x plus 1 plus 4x cubed times the square root of x plus 1, right? This exponent right here means put that down in the denominator and have it be a square root. And because I have 1/2, I can write it as just 2 in the denominator, which is the same thing. So really the only thing that's left in the numerator is the x to the 4th. So I need to get a common denominator here by multiplying this by 2 root x plus 1 over 2 root x plus 1. Okay, so that is going to give me x to the fourth over 2 root x plus 1 plus, now when I multiply these things, I am going to choose to combine the 4x cubed and the 2 to be 8x cubed. And then I am going to combine the x plus 1 and the x plus 1 in the square root, because when I multiply those things, I'm just going to get x plus 1. And that's all divided by 2 root x plus 1. So then y prime is going to equal x to the fourth plus 8x to the fourth plus 8x cubed, all divided by 2 times root x plus 1. So y prime is going to equal 9x to the fourth plus 8x cubed over 2 root x plus 1. And from there, 9x to the fourth plus 8x to the cubed, it's not too hard to see that that is going to simplify to a. So I'm going to end up with a as my solution there. So the calculus was done here, but the algebra is quite challenging to get it into that form. Number 11. Oh boy, this is a great problem. So this looks like we are dealing with a chain rule here. Anytime you have a trigonometric function to a power, I would encourage you to rewrite it as cosine of 4x all to the fifth power. Okay, so our outermost function here is blob to the fifth power. The next layer is cosine, and then the final layer is 4x. So we need to take the derivatives of something raised to the fifth power, then cosine, and then 4x. So this is going to be a double chain rule, basically. So let's take the derivative of the something to the fifth power. And we would get 5 times that something to the fourth power. Next up, we need to multiply by the derivative of the next layer. The next layer is cosine. So we're going to multiply by the derivative of cosine, which is negative sine of 4x. Now we need to multiply by the derivative of the last layer, which is 4x. So that's times 4. Now we're done because there's only 3 layers here. Blob to the fifth, then cosine of blob, and then 4x. So we're going to simplify this to, well, 5 times 4 times negative 1 is negative 20 cosine to the fourth of 4x sine of 4x. And that would be a nice and correct way to write it. This is not fully simplified because you really, especially if something is so easy like that, you need to definitely multiply the 4 by the 5 and get the 20. And it's nice to move this negative out front so you have the negative 20. So that's a nice double chain rule problem. Here they're asking us to find y double prime if y equals cosecant x over 2. So I would start by just saying y equals 1/2 cosecant x, so I can recognize that as a constant multiple or coefficient. So then y prime would be simply 1/2 times the derivative of cosecant. And the derivative of cosecant is negative cosecant x cotangent x. Make sure you have the x's in both places there. You can't just write sine with nothing in it or cosecant with nothing in it. It has to be cosecant of x, sine of x, right? There has to be an argument inside that function. So I'll rewrite that as y equals negative 1/2 cosecant x times cotangent x. So y double prime would be the derivative of that, which is negative 1/2 times the derivative of cosecant x cotangent x. So now I'm going to have to use the product rule because I have cosecant x times cotangent x. So I'm going to do first times the derivative of the second, and I'll just write it out so I don't have to do everything at once, plus the second times the derivative of the first. Okay. So y double prime equals negative 1/2 times cosecant x. The derivative of cotangent x is negative cosecant x cotangent x. No, it's not. That's wrong. Okay, the derivative of cotangent is negative cosecant squared x. Okay, and then plus cotangent x times the derivative of cosecant, which is negative cosecant x cotangent x. Okay, so y double prime is equal to. So I'm noticing that there's a negative here, here, and here. So when this distributes through, all those negatives are going to be gone, right? Because negative times a negative is a positive. So everything's going to turn out to be positive. So I'm going to just make everything positive now. It's going to be 1/2 cosecant cubed x, right? Because cosecant x times cosecant squared is cosecant cubed x, or cosecant x all cubed. And then plus 1/2 cosecant x times cotangent squared x. That would be a fine way to leave your answer, in my humble opinion. You could factor out a 1/2 cosecant x. You don't really need to in this case. That looks good. All right. Ooh, lovely. F of x equals tangent of 5x plus x squared. We want to find the second derivative. Okay. Now, first of all, don't make this more complicated than you need to, because we're just going to take the derivative of this, take the derivative of this, and add them. So don't be too tripped up by the x squared. The x squared is easy to take the derivative of. Let's find f prime. F prime of x would be, so we're going to take the derivative of tangent of 5x. That's a classic little simple chain rule problem. So we're going to take the derivative of tangent, leave 5x alone. Derivative of tangent is secant squared. Okay, and now we need to multiply by the derivative of the inner function, which is 5. Okay, and then we need to add the derivative of x squared, which is 2x. Okay, so f prime of x is going to be 5 secant squared of 5x plus 2x. So now we need to find the second derivative by taking the derivative of that. So we're gonna get rid of this because that's almost identical to f prime. That's definitely not f double prime. Um, so it's definitely not going to be that. Whoopsie daisy. Definitely not going to be this. Okay, good. Now let's find the second derivative. So I'm going to rewrite f prime as 5 times secant of 5x all squared plus 2x. So this friend right here is a double chain rule, because I have something squared, that's the outermost function, then secant of something is the next layer, and the last layer is 5x. So when I take that derivative, I'm going to have to use the chain rule twice. So f double prime of x is now 5 times 2 times secant of 5x to the first power times the derivative of secant, which is secant of tangent x, 5x, times tangent of 5x. And then I have to multiply by the derivative of 5x, which is 5. So that's the derivative of this right here. Now I need to take the derivative of 2x, which is just 2, so plus 2. So f double prime of x is equal to, well, let's see, 5 times 2 times 5 is 50. Then I have 2 secants multiplied, so secant squared of 5x, tangent of 5x, plus 2. So that is, that looks like that's D. So it looks like D is the correct answer there. 14, quick one. Given this limit represents f prime of c, aka the derivative of a function at a point x equals c. For a function f of x and number c, find f of x and c. I think this should be a comma, but that's okay. Okay, find f of x and c. All right, so we know that this should look like the limit as h approaches 0 of f of x plus c minus f of c all over h. So we're looking here and we're trying to find f of, so not f of x plus c. That's wrong, Alden, you silly, silly goose. Okay, let's try that again. That would be the limit as h approaches 0 of f of c plus h minus f of c all over h. So we're looking for this to be f of c plus h, where c is some value. Well, you can look here and see something plus h. So it looks like c is going to be -2, and then because you see the -2 plus h in there, and then we need to see what the function is. It looks like f of x is going to be 2x cubed minus 2x minus 2. And we can check and see if f of c, see what, sorry, not f of c, but f of -2, which is my c value, see what that is. F of -2 is -16 plus 4 minus 2, which is -14. And so you can see that that -14 matches this -14 when I plugged that -2 in. So that's my f of c. So there is my function and my c value. So this limit would actually equal f prime of -2. And since f prime of x is 6x squared minus 2, f prime of -2 would equal 4 times 6, 24 minus 2, which is 22. So this limit, if we simplified it all the way down, would actually simplify to 22. Okay, we're on page 4 of 5. I know it says 4 of 6, but there's only really 5 pages of problems. Functions f and g are differentiable for all real numbers. The table below gives values of the function, their first derivatives at selected values of x, with a being a constant. If h equals sine of f, write an equation of the line tangent to h at the point where x equals 1. Okay, so if we want to ever write the equation of a line tangent to a function, we need to find the derivative. H prime of x is equal to, not sine, Alban. Use the chain rule here. Take the derivative of the outer function, leave the inner function alone. That's going to be cosine of f of x, and then we need to multiply by the derivative of the inner function, which is f prime of x. So therefore, h prime of 1 is equal to cosine of f of 1 times f prime of 1, which is cosine, let's see, f of 1 has got to be 3 pi fourths times f prime of 1. F prime of 1 is the square root of 2. Now, cosine of 3 pi fourths, so 3 pi fourths is over here, so it's going to be a negative root 2 over 2. So this is going to be negative root 2 over 2 times root 2, which is -1, right? Because you get negative 2 over 2, so that'd be -1. So the slope is -1. So if the slope is -1, we also need to find h of 1 to have a y value. And what is h of 1? Well, h of 1 would be sine of f of 1. And f of 1, again, was 3 pi fourths. So that would be sine of 3 pi fourths, which is positive root 2 over 2. So there's our point. Our point is 1 comma root 2 over 2, and our slope is -1. So we'd write y minus root 2 over 2 equals -1 times x minus 1. And we would get this right here as our tangent line. Okay, now we move on to B. Find r prime of x at x equals 2, aka find r prime of 2. Okay, well, r of x is equal to g of 2x to the -1/2. So that's the first thing we'd want to do, is just write that as g of 2x to the -1/2, because I definitely don't want to use the quotient rule on this. This looks like a double chain rule again. Your outermost function is something raised to the -1/2. Then your next layer is g, and your final layer is 2x. So r prime of x in this case is going to be -1/2 times, leave the inner function alone, g of 2x to the -3/2. Now I need to multiply by the derivative of the next layer, which is g prime of 2x And finally, I need to multiply by the derivative of the last layer. And the last layer is 2x, so I got to multiply by 2. So if I simplify this a little bit, I should get r prime of x is equal to basically negative g prime of 2x divided by g of 2x to the 3/2 power, right? I'll just move that down there. I can multiply, of course, the 2 by the negative 1/2, and they kind of cancel each other out, so you just get -1. I left this guy in the numerator, and I moved this one down to the denominator because it has a negative exponent. Great, good for me, good for me. Okay, so now I can plug in 2. So basically, r prime of 2 is just going to be negative g prime of 4 divided by g of 4 to the 3/2 power. So r prime of 2 would be, so g prime of 4 is something like 9. So -9. And g prime of 4 is 3. So, man, I'm disappointed that this isn't going to work out nicer than it does, but that's fine. So g of 4 is 9. So that would be -9. Wait, no, that's g prime. Oh, I messed that up. Okay, g prime of 4 is 3. So it does work out nicely. -3 over g of 4 to the 3/2, which is 9 to the 3/2. Okay, and 9 to the 3/2 is the square root of 3, square root of 9 cubed, which is 3 cubed, which is 27. So that's -3 over 27, or -1/9. That's r prime of 2. Okay. All right, looks like we've got some implicit differentiation. No, we don't. We don't. These are still explicitly defined functions, so no implicit differentiation yet. Okay, friends, again, if you have a trig function like sine squared, I'd encourage you to write it as sine of x all squared minus cosine of x all squared. Now, I wonder if we could do a little simplification here. Not sure if this would be nicer or not, but I'm curious to say, hey, let's let y, I don't know why this is not writing, equal y equal sine squared x minus cosine squared is 1 minus sine squared. You don't have to do it this way, but I just think it's a little bit nicer. There's probably even a slicker way to do this. So I'm going to make this actually 2 sine squared x minus 1, because I just think that's a little bit easier to take the derivative of. So now I'm going to write it as 2 sine x all squared minus 1 and take the derivative, dy dx. So dy dx, the function that gives me the slopes for this function, take the derivative of the outer function. So that would be 2 times 2 sine x to the first power times the derivative of sine, which is cosine x minus 0. And that's just 4 sine x cosine x. You'll get the same thing if you do it another way, but that's one way to do it. Just simplify it first using the Pythagorean identity. All right, I'm going to erase this here so it's out of my way, but we'll remember that that was -1/9. Okay, this is going to need to probably use the quotient rule. So I'm just going to go ahead and do that. dy dt is equal to low d high. 1 minus sine t is the bottom times the derivative of the top, which is negative sine t, minus high d low. Cosine times the derivative of 1 minus sine, which is 0 minus cosine, all divided by 1 minus sine t squared. Never multiply that out. It's almost never the right idea. Just leave it. Okay. I mean this denominator. You should just leave as something squared. Okay. So simplifying this, we're going to get negative sine t plus sine squared t plus cosine squared t divided by 1 minus sine t. But this right here is 1. So we're going to get Whoops, that's squared. We're going to get dy dt. Dy dt is equal to 1 minus sine t, because again, that's 1. So negative sine t plus 1 is the same as 1 minus sine t over 1 minus sine t all squared. You can cancel one of those and get 1 over 1 minus sine t. So that would be your derivative dy dt. Okay, 18. We've got a composite function with a quotient inside. So dy dx, take the derivative of the outer function, leave the inner function alone. Then multiply by the derivative of the inner function. I'm just going to write ddx of 1 minus x over 1 plus x for now. Okay, so then dy dx would be 5 times 1 minus x over 1 plus x to the fourth power. Now we're using the quotient rule. Low d high, the derivative of 1 minus x is negative 1 minus high d low, 1 minus x times the derivative of the bottom, which is 1, all over the denominator squared, or 1 plus x squared. So we're going to get 5 times 1 minus x over 1 plus x to the fourth power times, let's see here, we're going to have negative 1 minus x minus 1 plus x. So I'm going to go ahead and get rid of the x and the negative x and combine the negative ones to get negative 2. Negative 2 over 1 plus x squared. I can multiply the 5 and the negative 2 and get negative 10. And then I'm just going to write it as negative 10 times 1 minus x to the fourth power divided by 1 plus x to the sixth power. And that's because I have 4 of them here and 2 more here. So that might be a good way to write dy dx. All right, and finally this one. Ooh, what a lovely problem. Let's rewrite y as x plus sine of x all squared, all to the negative fifth power. So the outermost function is to the negative fifth. So dy dx, using the power rule, is negative 5 times x plus sine x all squared to the negative sixth power times the derivative of the inner function. And the derivative of that is 1 plus, right, the derivative of x is 1 plus, now the derivative of sine squared, or sine x all squared, is 2 times sine x to the first power times the derivative of sine, which is cosine. Okay, so dy dx is then going to equal negative 5 times x plus sine squared x to the negative sixth power times 1 plus 2 sine cosine. And then I'll probably just leave it like that for now. Okay. All right, last page here. 10-foot ladder leans against a wall at an angle theta with the horizontal as shown in the picture. The top of the ladder is x feet above the ground. Okay, I don't know why my pencil's not working. I think I turned it off accidentally. So x feet above the ground. If the bottom of the ladder is pushed toward the wall, find the rate at which x changes with respect to theta when theta equals 60 degrees. Okay, the rate at which x changes with respect to theta is dx d theta. Okay, so that's what we're interested in. So because we're interested in relating x and theta, let's write an equation that would relate them. And the equation that would relate them, since we know the 10-foot ladder, is opposite over hypotenuse sine. So I know that sine of theta is equal to opposite over hypotenuse. So that means x is equal to 10 sine theta. So what I can do is now take the derivative of this with respect to theta, and I get dx d theta equals 10 cosine of theta. Okay, so I'm going to use radians here. Theta equals 60 degrees, so I'm going to say theta is pi thirds. Plug that in, and I should get dx d theta is equal to 10. By the way, if theta is increasing, which it is, because as I push this in, that angle's going to get bigger, I expect x to increase as well. So hopefully this is going to be positive. So 10 cosine of pi thirds. Okay, so pi thirds is right here, and the x value there is 1/2. So the cosine value is 1/2, so that's going to be 5, and the units would be feet per degree. So this thing extends by 5 every degree. Now I will say it doesn't make a whole lot of sense because it's not actually going to go up 5 feet, but if you did a tiny fraction of a degree, then it could go up by a tiny fraction of 5, and that would be okay. Okay, finally, we've got some implicit differentiation, and then I'll be done. So how do I know this is implicit differentiation? Because there's no easy way to solve for y. That would just be a mess. So we're going to take the derivative of both sides. d dx of y squared minus 3xy plus x squared should equal d dx of 7. Now, remember that if you take the derivative of y squared, that's like taking the derivative of g of x all squared. So it's a function inside the squared function. When you take the derivative of that, you get 2 times g of x times g prime of x. So when we take the derivative of y squared, we get 2 times y times the derivative of y, which is dy dx. So let's not forget that we use the chain rule there. Okay, and also when we have x times y, we're going to have to use the product rule. So what are we going to get? We're going to get 2y dy dx minus 3 times the derivative of xy. First, derivative second plus second times the derivative of first, which is 1. Okay, plus the derivative of x squared with respect to x, which is just 2x, and that all equals 0. So the calculus is done at this point. Now it's just algebra to solve for dy dx. So what we're going to get is dy dx times 2y minus 3x, right? There's the 2y, there's the minus 3x, okay? And then if I distribute this, I'm going to get minus 3y plus 2x equals 0. So I'm going to add 3y and subtract 2x from both sides, and I'm going to get dy dx times 2y minus 3x is equal to 3y minus 2x. So then I'll divide both sides by 2y minus 3x. My notation here is a little bit messy, but that ends up being my dy dx. 3y minus 2x over 2y minus 3x. I just kind of ran out of room. So that's what we would end up with there. Okay, take the derivative of both sides. Make sure you apply any rules. When you take the derivative of y, make sure you multiply by dy dx. And then, whoopsie daisy. And then isolate dy dx and solve for it. Or yeah, factor if you need to. Move dy dx to one side, factor, and then divide. Okay, blah, blah, blah. Okay, I'm going to erase this now so I have some more space to do this other problem. Woo. Okay, so this one right here, again, no easy way to solve for y. So I'm going to just take the derivative implicitly. So d dx, the derivative with respect to x of tangent of 5 plus y all cubed has to equal the derivative with respect to x of x. So the derivative of tangent of 5 plus y all cubed, we're going to have to use the chain rule twice because the outer function is cubed. The next layer is tangent, and then you have 5 plus y. So let's take the derivative of that and get 3 tangent of 5 plus y all squared. times the derivative of tangent, which is secant squared of 5 plus y, times the derivative of 5 plus y, which is 0 plus dy dx. Okay, and that equals 1. So instead of writing 0 plus dy dx, I'm just going to write dy dx. I just wanted you to make sure that I am taking the derivative of 5. It just happens to be 0 because it's not changing as x changes. So now I just need to divide everything by this. Now tangent is sine over cosine and secant is 1 over cosine, so it doesn't really simplify too nicely. So we're just going to say dy dx in this case is equal to 1 over 3 tangent squared of 5 plus y, secant squared of 5 plus y. We could also write that as 1/3 cotangent squared of 5 plus y times cosine squared of 5 plus y, which is probably a little bit nicer because there's no real good reason to keep tangent and secant down in the denominator when we can just put their reciprocals in the numerator. Okay, finally, determine the slope of the tangent line to this graph at this point, and then find the equation of the tangent line at that point. Okay, slope of the tangent line, we got to find the derivative. Finding that implicitly, we get 2x plus 8y dy dx equals 0. Do not solve this for y. That would be a mistake. You could do it that way, but it's not the most efficient way to do it. Okay, so we're going to get dy dx is equal to negative 2x divided by 8y, or dy dx is equal to negative x over 4y. So now we're going to plug in our point. At this point, dy dx would be, whoops, dy dx evaluated at square root 2, negative 1 over root 2 would be negative x, 1 over root 2 divided by 4y, 4 root 2, which is the same as 1 over root 2 times 1 over 4 root 2, which is 1/8. So that's my slope. Equation of the tangent line would be y. I plugged in the wrong values, didn't I? Oh, let me get rid of that. Gone. Try it again. It would be negative x. Come on now. There we go. Negative x, which is negative root 2, divided by 4 times negative 1 over root 2, which is negative root 2 over negative 4 over root 2, which is 2 over 4, which is 1/2. Okay, so the slope is actually 1/2. Okay, so slope is 1/2, so now I can do y minus 1 over root 2. Just kidding, it should be plus because I'm subtracting a negative, equals 1/2 times x minus square root 2. And there is the equation of the tangent line at that point. All right, well, perhaps that was helpful.